Yes.
So, what is today's topic? Anyone knows?
Sir, KTG.
Sir, KTG.
Oh, it's KTG.
Yes.
Oh,
Yes.
I thought it's semiconductor. Okay. So KTG is called kinetic theory of gases. So what is the meaning of kinetic? So we always come across the two terms kinetic and kinematics. So kinematics is called study of motion without considering its cause. So you only talk about the motion and you're not worried about who has caused the motion, who has changed the motion. If you have given you have given acceleration, you can find the velocity as a time function. So when you write V equals to U plus AT, do you really talk about who has produced A? The answer is no. You are just happy with A, whatever is given to you, and you go along with the formula. So that's called kinematics. What is kinetic? So again, it is a study of motion. Considering its cause. And this you have studied as a separate chapter in physics called Newton's laws of motion. So when you were studying the Newton's laws of motion, actually you were studying kinetic. And now our present topic is says kinetic theory of gases. So we are going to investigate the cause behind the motion of gases molecule. So how they move, why they move, what are the constraints they have in motion. So all those things we are going to consider. That's why it's called kinetic theory of gases. Now the question is why we need to study this kinetic theory of gases. So KTG is also called statistical physics. Now you may be wondering what is statistical physics. So the word statistics you have studied in mathematics, right? There's a chapter there. There you study about the mean, average, whatever it's standard deviation, variance, frequency distribution, and so on. So all those studies are actually meant for ensemble with a large number of particles or a population with a large number of some event. You record those events, you create a histogram, you create a pie chart, you create a bar graph, and so many other things. So the word statistical talks about a large number of data. And it uses a theory called theory of probability. So statistical physics is basically a physics which is based on the theory of physics based on the theory of probability. Understood? Now the question is why we need to study the probability. The answer is very simple. We know how to solve simultaneous linear equation of two variables. So if I give you a1x plus b1y equals to c1 and a2x plus b2y equals to c2, where x and y are variables, so these are two simultaneous equations. And you know how to solve this equation, isn't it? So when you were studying the laws of motion, So you were solving 2-block problem or 3-block problem, and you were writing the equation of those moving blocks or the wedges, and you used to get some certain number of equation. Maybe maximum I think you have come across is 6 or 7 equation, right? Not more than that. So the idea is, if you find the solving, even 3-variable equation, it is really tedious. If I give you equation in 3-variable, then this is going to be slightly difficult because now you need 3 equation, isn't it?
Yes, sir.
Because we need number of equation equivalent of number of variables, right? So if I consider 1 mole of gas, and because we are trying to study the kinetic theory, which means you're trying to talk about the actual cause of motion. So you need to write the force equation. You have to draw the ABD. So in 1 mole of gas, how many ABD we need to draw? Of the order of. So now tell me by common sense, is it feasible to solve these many simultaneous equations?
No, sir.
Present quantum computers, they won't be able to solve these many questions at one go. So no processing power of supercomputer that we have developed so far, even if we employ all the supercomputer across the world, and if we apply parallelly to solve this or these many simultaneous equations, they will fail to solve such equation. So the simple logic is, such a vast number of variables cannot be studied individually. Okay. And when you fail to study something individually, then you start estimating the behavior. And because you want to estimate something, you start creating some estimation parameters like mean, RMS. Okay. So these mean, RMS, the term which you come across, are basically a parameter which we employ to create some estimate about a given ensemble or given system. So KTG is not only about the gases. KTG is a very generalized theory which can be applied to any situation where the number of variables exceeds a certain large number. It is really like infinity. So you can apply this KTG idea for the electron in the conductor. You can apply the KTG in, of course, a gas in a container. You can apply KTG for the entire population of the world. You can apply KTG in a lottery system when the lottery is played across the world. You can apply the KTG in all the online, this number game. Okay. You can apply the KTG for the how the fans will react in the world who are playing, like football or like cricket. Anything which is having the infinitely large number of parameter that can be studied on the KTG model. So KTG is a model, a way to study things like that. Okay, and it has nothing to do with the only physics. KTG is you can say it is applied mostly in share market also. It is applied for studying the fluid behavior, liquid behavior, you can say gas behavior, or any behavior in which a large number of molecules are present. Okay. Or even the data. So we also play with the data, and the same KTG when it comes to the data science, it becomes the machine learning strategies. So everywhere there is a KTG. The entire statistical physics is the base of entire artificial intelligence or the modern day machine learning algorithm. So if you really understand physics part, you will have the advantage of understanding the real life application. Okay. So if we have an e-commerce website, and if they want to sell some product in a certain country, they look for the behavior or the pattern of the buying pattern of the consumers. and they apply the statistical model to get the right product for the right reason. Okay. So the question is why this mathematical model will mimic the real life behavior. How we can say that, okay, a mathematics is as good as real life. So I'll give you a simple example, which will perhaps help you in understanding why these statistical ideas work really well for the large population. So let's say you go and watch some movie in a theater. And generally, if you go and watch a movie, there are two exit gates, right?
Yes, sir.
See, get one, that's called exit gate 2. And imagine we have a sitting arrangement. Okay. And audience are there. So once the movie is over, let's talk about the mathematics. So if we have only two gates for exit, what is the probability that you will go from gate 1 and gate 2? What mass is? The probability of coming out of each gate is how much?
0.5.
Half.
Ah. So there are two answers. It is either a 1/2 or you can say 0.5. Okay, both are same answers. Now, let's say this movie is a really flop movie, and we have few number of audience. One is here, other is here. Or let's make it even number there. It's a very flop movie. So what do you think? Will they follow the maths and will go half will go from gate 1 and half will go from gate 2?
No,
Or
sir.
all will come from the exit 2 because it's nearby?
Yes, sir. Possible.
Second.
Unless I will say, okay, there is a toilet here and you want to go after, so this will go and will, okay. But the thing is, the maths and the real life, are they matching?
No.
No.
You can see it's not matching. Because we don't follow maths. But imagine it's a super hit movie. Tell me some super hit movie which has come in the last 10 years.
Drishyam.
Drishyam, okay. Okay, fine. So now we have the house full. So many. Now what will happen? Once the movie is over, will they follow the only exit 2 or someone will go to exit 1 also?
They will go to exit 1 also.
One also.
No, they will not ask you. I mean, do you ask the gate 1, should I go from this machine saying, okay, half and half? Still, they don't follow mathematics, but see, without saying, because of the crowd or the rush, they naturally starts coming in large number here and here also. till the crowd is really high. Okay. But again, towards the end, you may have some difference. So all will go from here. But towards the end, right? But mostly, if I say if there is a total capacity of 500, because it's a super hit movie, I can say 300 will go from here and 250 from here, 200 from here, right?
Yes. Yes, sir.
It is close to what, 0.5, if not exactly 0.5.
Yes, sir.
Now imagine if I add 2 more zeros, okay, and then the difference is, let's say, a difference of 5,000 will be there. So we have how many we have? We have 50,000. So we have 24,000 from here and 26 from here, 24 from here. Because only at the end, now you can see the answer is even more close to 5.5, right? So if I keep on adding zeros, and if I really add 23 zeros or 20 zeros or 10 zeros, you can clearly see that a large population starts behaving as math would have predicted, isn't it?
Yes, sir.
And it goes without saying, which means an individual can be erratic in its behavior, but there is always a static, or you can say steady behavior of the crowd. So in a way, a crowd always behaves in a predictable manner. So when we have a large e-commerce company like Amazon, and they have a consumer base of millions, they play with the rule of mathematics. They don't go by the rule of real life. When you go to, let's say, Los Angeles, and there we have a large number of casinos, they don't look for the everyday loss or gain. They go for the 1 year loss and 1 year gain, and they know that in 1 year, so many customers will come, someone will win, someone will lose, and they again take the statistical measure to understand that what is going to be profit at the end of this. So every game designer, okay, of course, they don't design game on their own. They consult the world best statistician from the Harvard, Stanford, and they design a game, okay, which you play, you may win, but if it is played over the years, only the casino will be the winner. An individual cannot be the winner because you are not part of statistical physics, but a crowd is part of statistical physics or mathematics, so to say. So this nature is inherent, okay, that a large ensemble or any population which is really large, their behavior is quite predictable. And that is why we take a small, you can say, part of a large population, which is called sample. We try to collect a various sample, and we study each sample, and we try to derive some correlation between the sample. And using the sample, we go back to understand the behavior of the population. So when there is a exit polls or opinion polls, whenever there is an election, they again use the statistical model. And the theory of probability is not only for this. If you go to some century, and let's say the number of population of tiger is decreasing, and you must have heard that, okay, this year the population has increased to this value. So do they really go and count each and every tiger in the entire jungle? Or is it possible to find every tiger in the jungle? The answer is no. You can't go to the Amazon forest and find every such species of certain animal. So what exactly they rely on? So again, they rely on the small number of sample, and they try to predict the behavior of the population by studying about the sample. Okay. So they might go to some location and they tag the animals. So let's say in over the year, they tag 1,000 of such animals, and they know the entire area of the jungle. Okay, so you know that this is the area of jungle. and you tag 1,000 some animal species. Again, this animal will go randomly in all directions. Over the years, they will distribute evenly. We can assume that, okay, the distribution is even. Okay. And then one fine day, again, you come after 1 year to the same spot, and you see there are 25 such tagged animals. Now, because we know that it is uniformly distributed, so by dividing the area in equal value as this spot, I can exactly count the close value of the total number of animals. Let's say if we have 100 such clusters of same spot area, then we know the total number of tiger is actually 2,500. Again, these are all statistical modeling methods. So there is a huge scope of statistical physics, and it is the biggest branch of, you can say, science nowadays, because we are dealing with a really huge number, large numbers, and the entire game industry, this betting industry, they all rely on the statistical model or simply the theory of probability. And now we have added some deep insight to their models using the machine learning and artificial intelligence, which are having the backbone with statistics only. So this is the like overall preview of the chapter. Why we are studying? I mean, the why question is clear, I hope so. Why you're learning this KTG? Now, if why is clear, then it's easy. Why you're going to learn? So you're going to learn about the gases behavior, but is it possible to study the behavior of individual gas?
No.
So when you fail to study the behavior of individual gas, you create on an average behavior. You create something called macroscopic behavior. Okay. So we are going to study now the average behavior of the molecules, not individual behavior. And KTG is a method or a model by which you attack the problem. And because it's a model, it means it is some sort of hypothesis. It is some postulate actually. So you need to know what are the underpinnings or the postulates over which this model is based on. So what are the do's and don'ts that we can apply, we cannot apply. So once you know these do's and don'ts, it's very easy to actually decode this entire chapter. If you know the do's and don'ts, it's very easy. So we are going to study something called the postulates of now. A postulate is what? What is postulate? A postulate is basically some set of assumptions, right? Very good. So postulate is basically some sort of assumptions, and these assumptions are kind of scientific, not some random assumptions. And following these assumptions, we create a model, and following the model, we predict the other behavior, and that is how you design the entire world of a new science. So thermodynamics or KTG or entropy, all are based on this statistical model only. But what you see as a beginner, the top layer, the macro behavior, and you don't get a chance to study the internal working. So it's really exciting to, I mean, for me, teaching this subject itself is very exciting. And learning should be also equally exciting because you're going to see something more deeper, and many myths will be burst today. And now you will today understand what exactly is pressure, what you call temperature. Okay. So all this terminology which you have been using in chemistry, in physics, the myth will burst and you will realize what exactly is all these variables. Okay. So the postulate starts with something very simple. Okay, I will just dictate the postulate. I will share the notes, you can read about it in detail. So the first postulate says that, okay, that every gaseous molecule will behave as a perfect rigid sphere. Now, saying as a every molecule as perfect rigid sphere will make no difference because they are so small that even if you think that no sir H2O is like this, I'm saying this is the hybrid diagram or you can say actual configuration, but how it will appear to the observer? Will it appear like this or like a tiny dot? Because it is so small that it is eventually like a sphere, isn't it? So assuming any molecule as a sphere is a good assumption. I won't say it's a wrong assumption, isn't it?
Yeah.
And the actual configuration doesn't matter for the size of the molecule. So actual configuration is only meant for the chemical reaction. We need to know this actual shape of the molecule so that we can also understand whether it will undergo the SN1 reaction, SN2 reaction. Is it easy to attack at the nucleophile site or the electrophile site? So all those attacking of mechanism requires the idea of the actual shape. Okay. But when we are talking about the motion, we are going to discuss about the motion. So when it comes to motion, then what we should know is a single particle, and a particle-like assumption will make it easy, to formulate the laws of motion. So this postulate, this assumption, or the first assumption of this postulate is, I think, logical. I won't say there is anything illogical in this assumption, isn't it? So
Yes.
what we're going to assume, every molecule is going to have what?
Perfect rigid sphere.
Perfect rigid sphere. Okay. Now, because they are rigid, which means it cannot deform. And because they cannot deform, so there is no question of inelastic collision, right? Because in inelastic collision, deformation happens. We lose some energy in the process of deformation. And that is why the kinetic energy of a colliding particle before and after are not same, because some amount of energy goes in deformation, or you can say potential energy conversion, apart from the heat and all. Okay. So what kind of collision they will undergo? Because it's a perfect rigid sphere, so we can say that collision must be perfectly elastic. And if collision is perfectly elastic, then what else will happen? Tell me. If collision is perfectly elastic, then what will happen?
Energy conserved.
Yeah, so the kinetic energy remains same, right?
Yes.
So they will undergo perfectly elastic collision. So if they collide with a rigid surface like a wall of container, then the speed with which you will hit the surface, you will reflect back with the same speed. And listen carefully, I'm saying speed, not velocity, because you may hit the wall at some angle, it will come like this, isn't it? So velocity is not same. What is same?
Speed.
Now this assumption is true if it is hitting the rigid surface. It will follow the law of reflection. So this assumption is making this possible, that the collision is going to be something like this. If you hit at theta, you will go at theta. The second is the volume occupied by the molecule is negligible compared to the entire container. It is like if in a room, let's say you are sitting in a room and suddenly two mosquito enters your room. They will not come to you and complain, see, it's very congested room. Because of you, I cannot move freely. Will they complain? The two mosquitoes entering your room?
No.
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 No, because for them it's an entirely empty room, right? So compared to the size of the mosquito, the room size is infinitely large. So coming of mosquito in even certain number will not make them feel suffocated. So every molecule will get how much space to roam? You can say the entire volume of the room is available for the mosquito to roam, isn't it?
Yes.
Yes.
So this is assumption, and the same assumption is not true when you go to the real gases, where you do consider the dimension of molecule, and therefore every molecule will have a lesser space to roam. So the first will get the entire volume, but second will get the entire volume minus the first volume, and the third will get the entire minus 2, and so the nth will get entire volume minus n minus 1 into individual volume, isn't it? And because you talk
Yes.
about the a very large number, so you say that the total volume available will be the volume of the room minus the number of molecules into volume of each molecule, right? And
Yeah.
eventually this is called the volume correction in the van der Waals equation, okay, which you study. And what we are going to study is the ideal gas situation. So I'll tell you what we are going to study. In our assumption, the volume is ignored. Okay. So every molecule will get the same volume to roam
Same.
around. Okay. So there is no difference of volume. And this is as per the postulate of KTG, as per the assumption of KTG, isn't it? The other thing there, it is said in the postulate that they do not interact with each other. They do not interact with each other except during collision. It means in the collision time they do interact, but beyond that they don't interact. So collision is of course a strong interaction of two particles for a very small interval of time. It's called collision, right? What is the definition of collision? Collision is basically the impulsive interaction, isn't it?
Yes.
So when two or more than two particles interact very strongly, but for very short-lived interval, we call such process as collision. And collision doesn't mean they must touch each other. There is nothing like touching. Just interact strongly. So if we have a charged particle, then they can repel from a distance, and still they have a strong interaction. So any impulsive interaction is called collision. And therefore, it is said in the postulate that they interact for very small duration. I mean, sorry, they interact. They don't interact at all except during the collision, and the time of interaction is negligible, almost zero. Now, what is the consequence of this statement of KTG? What we can conclude? They don't interact. They don't interact means they neither attract nor repel. Understood? And because they neither attract nor repel, it means, what does it mean?
Electrically neutral.
Pardon?
Electrically neutral.
Yeah, they are definitely electrically neutral. The lack of interaction actually signifies that such system cannot have internal potential energy. So any gas which follows the postulates of KTG, when you describe the internal energy of such system, you should be really happy because you need to just discuss the kinetic energy. The potential will never ever come into the picture. Because potential energy only comes when there is an interaction. So like for when two masses interact, we have gravitational potential. When two charges interact, we have the electrostatic potential. But if there is no interaction, can we have any potential energy? Yes or no? So
No, sir.
KTG says that there is no internal potential. Now, there can be a macro potential, which means if we have a gas in a balloon and if you release the balloon, let's say it's a helium gas. So you fill a balloon with helium gas and you release it, it will go up. So the entire gas as a system will rise up, of course, because of the density difference of the gas of atmosphere and the gas of the helium, it will rise up. So compared to the, if you take the entire balloon as a system and Earth as a reference, then the balloon as a whole potential is increasing, isn't it? MGH.
Yeah.
Yes.
But this potential is called the macro potential. This potential is defined for the central mass. But if you are in the CM frame, do we see any potential? The answer is no. So the MGH is called the potential energy of central mass. And what I am talking about in this particular scenario, that there is no interaction energy of the gaseous system. So there is no internal potential energy. Do you realize this, what I'm saying? So this internal potential is also called the microscopic potential energy. Do you realize this, what I'm saying?
Yes.
Yes,
So
sir.
microscopic potential is not present, but macroscopic potential is, or it can be defined as per the reference line chosen and the location of central mass of the gaseous system. Okay. So in this particular chapter, because of the assumption, there is no interaction and therefore there is no potential energy. But if you go to again real gases, the van der Waals equation brings a cohesive force into picture. And this cohesive force we take care by the symbol A, right? You have a symbol A in the equation.
Yes, sir.
E plus n square A by V square
Yeah.
into V minus NB equals to
Mm.
nRT.
And yeah. Yes,
What
sir.
what A signifies there, which is the attraction. So A is the attraction which does exist in the gaseous molecule. So real gas will have attraction. And why this A is so important in the context of real gas? So you might have heard about something called liquefaction of gases, right?
Yeah.
And there is a critical temperature and pressure beyond which only the liquefaction can take place, isn't it?
Yes.
Yes.
See, gas is always a gas. What is vapor? Vapor is those gas which can be liquefied.
Yes, sir.
Every gas cannot be liquefied. So just by increasing pressure can we liquefy a gas? The answer is no. Even if you make infinite pressure, gas will remain gas. Only below certain critical temperature, if you start increasing the pressure, at certain value pressure, it will change to liquid because the attraction is there. So eventually they start coming closer and change the phase. So when you increase the pressure below certain critical value, the liquefaction will take place. That's why those gases which can be liquefied is called vapor. So vapor is defined for any liquid, right? But every gas cannot be liquefied. So every vapor is a gas, but every gas is not a vapor. Understood? And that is
Yes.
why the A plays a big role in the world of van der Waals equation. So without A, we cannot think about the process of liquefaction. And that's why we have a critical value of pressure, temperature in terms of A and B, right?
Yes.
Yes, sir.
So which you can solve using the van der Waals equation. Anyway, that's part of chemistry. You must have done there. We are here concerned about the KTG part. So we'll go further deeper. So the lack of interaction will also eliminate the possibility of which energy form. So which energy form we cannot think present microscopically. Tell me, guys.
Yes, sir.
Which energy form will be absent microscopically in a gaseous molecule?
Potential energy.
So potential energy.
Potential.
Potential. Which potential? Internal potential, right?
Internal potential.
Microscopic.
Microscopic.
So potential, right?
What you also need to remember that the potential energy and the internal potential are two different aspects of saying it. So when I say internal potential, I talk about the one-to-one interaction. The in potential by virtue of interaction of individual gas molecule with each other. When there is a lack of it, it is absent. But when I say the word potential energy of a system, then we only consider the central mass. And if central mass is changing its position, we can say the potential energy is increasing. Understood? Sometimes it is also possible that we can convert the we can convert the external potential, we can say the potential energy, the bulk potential, into internal kinetic energy. Because potential we cannot make. And there are some questions in the J advance also, which they ask very simple question, that there's a gas container moving at a velocity v. Now, when I'm saying a container of gas is moving as a whole, as a system with velocity v, and if the total mass of the container is capital M, ignore the mass of the container, capital M is the total mass of the gas. So what is the total kinetic energy of this system? Half mv square. This half mv square represents which energy? Internal or external or macro?
So the macro one.
So it is the macro one, right? MACRO, right? So half capital mv square represents which energy?
Macro.
Macro energy. The motion of individual gas occurs at very high speed. And because of the randomness, can we assume the center mass is almost there?
Yes.
Yeah, we can say it. So when a container containing gas molecules moving with velocity v suddenly stopped, then where this energy will go? If it is suddenly stopped. So let's say there is a wall, a perfect rigid wall, and you collide with the wall and come to rest. So where this energy will go? Now, as I said, the container is massless. So there is no loss of energy because of collision. Collision only happens, in collision, energy is lost when there are two massive objects colliding. And what is colliding here? A massless container. So it will simply stick to the wall. And all of this energy we actually distribute to individual molecule as internal kinetic energy. So later on, you will come to know that this energy will actually consumed by each and every molecule, or you can say it will be distributed across the volume of container and will be gained by individual molecule. I mean, it will distribute among themselves. Okay, anyway, we'll come to that as when we solve the numerical. But right now, I hope the potential idea is clear. So for
Yes.
any gaseous system where there is no interaction, when you use the term internal energy, what do you actually refer to? What this internal energy refers to? Tell me. This
Sir,
internal
any
energy refers
type
to.
of energy which these gaseous particles in the system possess?
So this is the kinetic energy of the gaseous molecule, isn't it?
Yes, sir.
So internal energy of a gaseous system is nothing but the kinetic energy of gaseous molecule. So the microscopic kinetic energy having a name internal energy. But in the real gas, when I say the word internal, what it refers to?
Sir, both the kinetic energy and the internal potential energy.
Yeah, kinetic energy, internal potential energy, as well as some chemical energy also, because they do undergo some modification of bond, rearrangement of the bond also, right? Because they are real gas, they can interact, they can react also.
Yes, sir.
So quite possible that in a real gas scenario, they can have a reaction. And a reaction is what? A reaction is basically the reconfiguration of bond, right? You break some bond, you make some bond, so you lose some energy, you gain some energy, and there is a net energy change which is accompanied. So even a chemical energy also be part of internal energy. So theoretically, one should be aware that a real gas can have internal energy as a kinetic, potential, chemical, and so on. But the KTG part only talks about which energy? As internal
Kinetic energy.
only pure kinetic energy. It's only kinetic energy. Okay. Now again, the problem is in a simple in a container, even though it's a very rarefied gas, the number of molecules will be very large, isn't it? So even in a rarefied medium, the count of the molecule is going to be large enough. Yes or no?
Yes, sir.
Yes, sir.
And so the common question is that if the count is very large, can we really talk about the kinetic energy of individual particle?
No, sir.
No.
No, because they are constantly colliding with each other. So they are constantly exchanging the energy as well, isn't it? So some molecule will have less energy, some will have more energy. The total energy of the container is going to be same, but energy of individual molecule can be compared. The answer is no. We cannot talk about the individual energy. So what we talk about?
Sir, statistically, like the probability of a molecule having how much energy?
Probable
Yeah.
energy.
So what we do is, if you divide the container into infinite sub-container, or if you call it elementary container, so the infinity, because the number is so large that even in elementary container, the number will be. So as a whole, it is definitely infinite, but even for single elementary container, or you can say elementary volume, the number of molecules is going to be very, very large. And if you try to study statistically those number of molecules, then the velocity of those molecules, we'll say this is a fraction. So the velocity of those molecules will vary like this, something like this. Later on, this is going to be called Maxwell speed distribution. We'll come to that also. And F represents the fraction of molecule. So they are very small fraction, almost no zero fraction with zero velocity. So we don't have any molecule with zero answer. But as V will increase, the fraction will grow. And you can see there is one particular velocity which is having maximum takers. And what is this velocity we call?
Most probable.
Because this is having maximum probability. To have this velocity in a given subsystem, the probability is maximum, the fraction is maximum. And so there is a term called maximum most probable velocity. So the word most probable itself is statistical behavior, isn't it? Understood what I'm saying?
Yes.
Yes, sir.
Now, because we have divided the entire container into infinite elementary cluster, and if every cluster will represent the same graph, then we can say that for the entire container, the graph is same. Okay. And as I said, the kinetic energy of this cluster as a whole is going to be same as this cluster. Because in
Yeah.
this cluster, we have again, see, in every cluster, we have infinite molecule with a different value of energy. But the total energy of every cluster is going to be same.
Yes.
See, we are not saying individually, what we are saying cluster wise. And how many clusters we have?
Infinite.
So in a container, we have infinite cluster, and every cluster will have possess the same energy, because the kind of distribution that we can get here, without any biasness, I can say the similar distribution I'll get here, 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 here. So it is highly inconvenient to define the kinetic energy for cluster or for the system. So we thought of replacing this entire average behavior or average kinetic energy in a more simplified or dignified manner And that led to the definition of word temperature. So temperature is a macroscopic variable. What is temperature? And temperature is defined for the entire system. And when it is defined, it is only defined when the distribution of energy across infinite cluster are equal. Understood? And when
Yes.
this is the case, then we say the temperature of this system is T. So what is the role of temperature? The role of temperature is to tell me, guys. What is the role of temperature?
Sir, I don't exactly understand.
See, the kinetic energy of every cluster is same, right? But kinetic
Yes.
energy of every molecule is not same.
Yes, sir.
It is only same. See, it's like the family income is same, but not of individual.
Yes, sir.
And how
Yeah.
many families we have in this container?
Infinite.
We have infinite families, but almost all families are roughly same. So there is a
Yes.
replica of family, right?
Yeah.
Yes, sir.
So now talking about the kinetic energy of the family or for the system, we talk about the average kinetic energy of the gaseous system. And this average kinetic energy we express in terms of temperature. Or you can say temperature is the quantitative abstraction we use for kinetic energy. So instead of dealing with kinetic energy, what we deal with?
So temperature is like a representation for the kinetic energy,
Exactly. Yeah, the average kinetic energy. That's correct.
sir. Okay, sir.
Temperature is meant for the representation only. So there is
Yes, sir.
nothing like a temperature. Do we have something like temperature actually?
No, sir.
No.
We define temperature for
We define temperature. It means it must have some, more intrinsic way of saying it. So what you call temperature in chemistry, physics, or history, or civics, or geography, the word temperature was a kind of a monumental figure given to the word kinetic energy for the system. And the problem is the temperature of a system cannot be defined unless the families are uniformly distributed over the volume, isn't it? So let's say we have a high income group in this area. Let's see if I say this area is having high income families, and this is low income family. Can you define the temperature for the family as a whole?
No.
no, sir.
No.
Because this is like high temperature, this is like low temperature. So within a single box, we have two different temperature zone, which is not advisable. So if we have a different distribution of income in different location, then we'll be able to define temperature.
No, sir.
Yeah, you may define temperature for the cluster wise, but is it possible to define temperature for the system? Because
Not for
our
the
system is the entire container as a whole, right?
Yes, sir.
So therefore, we need some sort of equilibrium, right? We need some kind of equilibrium in order to define the temperature. Yes or no?
Yes.
Yes, sir.
So system as a whole must be in certain type of equilibrium. And when they have that equilibrium, when the kinetic energy is kind of distributed in this fashion, then the momentum exchange will be symmetrical, which means due to collision, whatever you will give it to me and I'll give it to you, that will change at individual level, but it will not change at the which level? Cluster level. Understood what I'm saying?
Yeah.
So
Yes,
let's
sir.
say in one cluster and there's a neighboring cluster. There are two molecules. There are two molecules. One with high energy, other with low energy. So this will hit this, and this will hit this. So one will lose, one will gain. The total energy of this part will be same. So the weaker guy from this will be beaten by the stronger from here. But we do have a symmetric pair. We have a stronger here and weaker here, isn't it? So in a fight between two clusters, what will happen? The weak. Strong. So let's say the blue is the weak and red is the strong, the angry guy. Blue is the cool guy. So the red will beat the blue. So when you get beaten, you will gain some energy. Yes or no? So a high speed particle is hitting the low speed. So the low speed will become faster than before.
Yes.
And therefore its kinetic energy will increase.
Yeah.
But in the same cluster, someone is going to lose also, right? So cluster wise, the energy changes zero.
Negligible.
0.
I mean, cluster wise, they are maintaining the energy, no? So
Yes.
even though they are undergoing constant collision, the cluster wise configuration is constant. Do you realize this?
Yes, sir.
Yes.
And the same configuration is repeating throughout the volume. And because there is a very kind of a steady state distribution of velocity across the entire container, and this is a final distribution. So for such scenario, you define temperature. You don't define temperature when the distribution varies across the volume. So when we define temperature? Only when the energy distribution has attained some
Constant.
Equilibrium.
distribution, right?
Yes, sir.
This equilibrium distribution of energy suggests that there is no further rearrangement. This is the best case scenario, right? Can we go further? Can we do better? The answer is no. So the best case scenario of a distribution in physics is called attaining the highest order of disorderness. Because this is the perfect symmetry. So can we say it is extremely random?
Yes.
Do you realize this? A symmetry is the extreme case of randomness.
Yeah.
So let's say you are going in a school, like it's a co-ed school. One side is all boys, one side is all girls. Is it symmetric distribution or highly asymmetric?
Highly asymmetric, sir.
Symmetry.
Because the probability of finding boys on the left side is 0 and girl on the right is 0. But if they sit in a completely random fashion, then can we count the equal number of boys and girls on each side?
Yes.
On
Yes.
each bench?
Yes.
In every quarter of the room?
Yes.
So a randomness is a way of saying symmetricity, isn't it?
Yes. Yes.
And symmetricity is the way of saying unbiasedness. There is no biased distribution, right?
Right.
And unbiasedness lead to the concept of what? The unbiasedness is the property of nature, and the extreme degree of unbiasedness, which means if you cannot be more unbiased than that, it means you cannot be more symmetric than that. It means if you cannot be more random than that, is called highest level of entropy. Because the word entropy means disorderness, right? So
Yes.
a system always try to go from a given distribution to a distribution with highest entropy, isn't it?
Yes, sir.
Because highest
Yes.
entropy means what? Highest disorderness, which means what? Highest symmetricity, which means what? The best unbiasedness.
Yes.
And mathematically, it means equiprobable event throughout the volume. So every event is equally possible, equally probable, isn't it? So
Yes.
can we understand that entropy is also probability? And the probability becomes what? Equal everywhere. So what is the end result or end goal of any dynamic system? What they want to achieve in their life?
Highest level of entropy.
Exactly. And the day it will acquire, the entire system will collapse. So nature prefers high entropy. And what we prefer?
Low.
The lowest. We see, do you want the, in your room, if you have books, you have kitchen, you have utensils, refrigerator is in the kitchen, everything is ordered or disordered?
Order.
Order.
So we are against the nature,
Yeah.
Yeah. Yeah.
isn't it? So we as a human, we want to keep things ordered, which is against the nature. Nature wants
Everything
disorderness.
disorder.
Because what is the probability of finding a book in the bathroom? Extremely rare.
Yes.
Or a soap on your study table? Extremely rare.
Yes.
Yeah, very rare.
So because things are ordered, no? So they have a high priority in the bathroom and almost zero in everywhere else, right?
Yes.
So ordered things are not way of nature, and disordered is the way of nature. So nature prefers disorderness because nature is unbiased. So it will not have a preference for someone and a different preference for others. It is symmetrical. It is disordered. And that is led to the concept of second law of thermodynamics. You will come to know that the entire idea of second law is to tell the world that how a system proceeds naturally. So any spontaneous system will proceed in a way towards higher entropy or lower entropy.
Higher entropy, sir.
Higher.
Common
Higher.
sense, because that is how the nature proceeds. So the nature is trying to go towards the higher entropy. Okay. So entropy having a very large number of definition. I mean, you know that entropy is the degree of disorderness or the inverse degree of orderedness, isn't it?
Yes.
But there is also
Yes.
one definition which none of you know about, that the entropy is the inverse degree of quality of energy. Oh my God, what is this quality? How energy can have a quality? So let's say you eat rice, dal, and Kit Kat. How you prefer eating all these three? Mixing rice with Kit Kat, or dal with Kit Kat, or rice with dal?
Rice with dal.
Option 3.
Option C. Now, whether I add rice to Kit Kat or dal to Kit Kat or rice to dal, in each case, the total cost of the food will be same.
Yeah.
So cost is like energy. So keeping Kit Kat with rice is ordered or disordered form.
This
It's a
one.
disorder form. Okay. So you said, okay, you eat first your meal, then you go for dessert. Now here things are mixed together. So when we have a system in which, let's say, if you're talking about your home, if you have a refrigerator in the kitchen, books in your study room, and things accordingly in their respective places, and there is a cost of this configuration, right? You buy things with a cost. Now, does it matter if I shuffle everything from the respective position to the random position? What will happen to the cost? Will it change or remain same?
Remain same.
Remains
But now we say that the quality has
degraded.
degraded.
Yeah.
This is a bad quality of ordering, right?
Yes.
So entropy represents a bad quality of energy. Yeah, it's a bad quality. But the irony is nature wants the baddest quality, the worst quality, not baddest, the worst quality of energy. Because the worst quality is the highly unbiased. Do you all realize this what I'm saying?
Yes, sir.
Yes.
So nature is having the inherent property to make things worst in quality because nature cannot be biased. So the orderness is not part of nature. So the second law came into picture because of this thing that why certain event happens and why certain event does not happen on its own. So heat flows from high temperature to low temperature and it doesn't ask you that should I go there or not. It happens on its own, yes or no?
Yes, sir.
Yes.
So when heat goes from high to low, it is called natural process. And because this is processed by the nature, it will always lead to which entropy change? High entropy, low entropy.
Hi.
So go to high entropy change. So when a nature undergoes any process without any effort externally, or we say if a process is spontaneous, like self-governing process, which we call spontaneous, the whole idea of self-governing process or any spontaneous process is to attain the highest order of entropy, or at least the higher entropy. So this was the explanation given that why certain processes occur and why certain processes do not occur in nature. And people were really curious about that. Why heat goes from high to low temperature, but not from low to high. It may be natural or intuitive that it goes, but why it goes? I mean, do you have the explanation for the same? Just because it is going for science since time immemorial, can we take this for granted or should we explain this to the world? We must explain to the world, isn't it? And
Yes,
that
sir.
led
Yes.
to the creation of second law. The second law was brought in order to explain to the world why certain things happens and why not certain thing happens. And then what? Then we have refrigerator, we have air conditioner, we have heat sink. All this we design against the law of nature. So we all know that heat will flow from high to low because that is how the nature works. So to let the heat to go from low to high, what we have to do? Because this is not a natural process. Now we have to perform this process, isn't it?
Yes, sir.
So what your AC is doing? Your room is cold, the outside is hot, and how the energy is thrown inside to outside or outside to inside.
Outside to inside.
Hmm.
No, it's sorry, inside to outside.
So to cool your system, what you do? You again take the energy from inside
Yes,
and
sir.
throw it outside. So the heat is going from where to where? Low to high or high to low?
Low to high.
So is it as per nature?
No.
And because it is not as per nature, so we need a machine which can perform this task. So we have AC, we have refrigerator, which are doing against the law of nature, isn't it?
Yes.
So when we need a machine, when we are trying to go against the nature, if we are doing something as per nature, we do not need the machine, it will happen on its own. So you take a soft drink which is chilled inside and put in a room, it will naturally acquire the room temperature after some time, isn't it?
Yes.
Yes.
Because that is as per law of nature, no?
Yes.
So the heat from surrounding will enter the bottle and it will make it warm.
Yes.
The next postulate. So temperature, you understand what is temperature? What is temperature? It is the measurement of, or you can say it is the way in which we express the kinetic energy of any gaseous system when it attains what?
Equilibrium.
Thermal equilibrium. So we call it thermal equilibrium. It means when the energy distribution or the velocity distribution will have same value throughout the elementary volume designed across the volume. So if you divide the entire volume into infinite sub volumes, we call it elementary volumes. And if every volume, if you go and observe the distribution of atoms or molecules there, and if the velocity distribution of every elementary part is similar, we say that it has attained the equilibrium. And in that scenario, you define a unique value of temperature. Because to represent one type of distribution, we need one variable of temperature, isn't it? So a particular type of distribution will have one temperature. So as the temperature will change, the type will, the shape will, the distribution graph will change actually. Okay.
Change.
So later on, this is called the Maxwell speed distribution. And in the Maxwell speed distribution, if you try to plot the graph, so as you increase the temperature, it will become more and more flatter, but it will spread more. So we'll come to that. So these represents a different shapes. So they will must have different equilibrium temperature. So different shape represents different equilibrium temperature.
Temperature.
And one shape represents the distribution of molecules in one cluster. Understood?
Yes, sir.
And the same shape will continue for the every cluster. Is it clear?
Yes, sir.
Yes.
And to represent one particular shape, we use one variable called temperature. Is it clear?
Yes, sir.
And as temperature will grow, the peak will shift towards the bigger value of V.
Yes, sir.
So a higher temperature system will have the most probable value on a higher side. Simple, isn't it?
Yeah.
And because the velocity graph is towards right, so as V will grow, the peak will shift towards right.
Yes.
And because later on we'll come to know that this area represents the fraction. So the total area must be same because the sum of fraction is how much? The sum of fraction is 1.
1. Yeah.
So the area will represent the sum of fraction, which is always 1. And therefore, no matter which graph you choose, we cannot change the total area. So as you spread, you must lower the vertical height, right? So as the graph will be flattened, the peak will come down, yes or no?
Yes. Yes.
Because what must be conserved here? The total area. Understood?
Yes, sir.
Yes.
So these are all questions which you will see in the chapter of KTG, that how temperature represents, what it represents. So one T represents one distribution of velocity. Understood what I'm saying?
Yes.
Yes, sir.
Yes.
So this is the KTG for you. Now the next concept, come to this. Every system will take some time to make the distribution uniform. Now let's say you have attained the distribution. I would like to talk about something called pressure. What is pressure? So we have a fast moving molecules And every moving molecule will have some momentum, yes or no? Because momentum is mass into velocity. All right.
Yes, sir.
Yes.
When this molecule will come near the surface of container, it will make some elastic impact. And as a result of elastic impact, the momentum will change. So if this is M, this is V, this is V. So what is the delta P here? Can we say 2 mv cos theta?
Yes, sir.
Because the velocity in the direction of impact is V cos theta. So you come with V, you go with V. What is the change in velocity or
Addition.
change in momentum? 2 mv cos theta, right?
Yes, sir.
And the molecule will be there for some small tiny interval, which is much smaller than your imagination. So there is a delta P and there is a delta T involved. So there is a force involved, yes or no?
Yeah.
And if you consider the entire surface area of the wall, so it will have some contribution to the pressure. This is called the partial pressure of each molecule. P1.
Yes, sir.
Yes, sir.
And because we have a large number of molecules, so we can say then total pressure on the surface will be how much? The sum of all pressure due to each, isn't it?
Yeah.
Because pressure is scalar. So can we add this pressure just like this?
Yeah.
And this becomes later on called the Dalton's law of partial pressure, isn't it?
Yes.
Yeah.
Now, of course, Dalton was not able to understand this KTG, but it is like we go in the, in the past and we try to explain those events again by this KTG. Okay. So you redefine every event which different scientists define in their time by a certain way. KTG is able to explain everything in common sense. That's the power of KTG. Okay. Now the question is, what is pressure? I mean, if there is no wall, it means there is no pressure. So if you go outside, out of your room, is the pressure zero outside or is it pressure there also? Is it pressure meant for the wall?
So pressure occurs on any surface.
So yeah.
And if there is
and,
no surface, there is no pressure.
So it depends on what the surroundings are.
So let's say if you go inside your room, tell me what is the pressure at the center? Is it zero or non-zero?
So zero, I mean, yes, a zero, sir.
It is zero.
non-zero.
So at the center, there's just air.
So that's why I'm asking, what is pressure? Is it air or is it wall? What is pressure then? So pressure is
pressure-
defined for only the wall. So if you go outside, so why you say the word atmospheric pressure? Because there is no wall.
Yeah.
So there's the ground.
And above the ground, there is no pressure. Atmospheric pressure is up to Everest also,
Yes, sir.
which
Yes.
is almost 8,000 meters above the ground.
Yes, sir.
It means we have so far we all have understood in a wrong way what is pressure, right? So you haven't understood the pressure at all.
Yes, sir.
Anyone who would like to explain pressure to me?
Sir. Pressure is a characteristic of like a particle.
Quite true.
Like you said in the example that pressure is 80 atmospheric pressure is there at the Everest also. So it depends on the particle and not on the wall or area.
So what is pressure? That's a big question. No?
Yeah.
Because see, unless we are not able to understand pressure, we cannot go further in the KTG. Because the KTG having the basis only on pressure only. Once you crack the pressure, you crack the entire chapter.
So,
Yes.
sir, pressure is the force exerted by any of the adjacent particles over an interface that's assumed
Hmm.
per unit area, that is.
Yeah. Pressure is basically, it's a way to say ability to exchange momentum whenever intercepted. These molecules are very powerful. They carry momentum. And the moment you intercept it, they will readily transfer their momentum to you. And if you calculate the momentum transfer per unit area, per unit time, then this measurement of transfer of momentum per unit area per unit time is called pressure. Because the rate of change of momentum is called force. So the other way of saying is the rate at which you transfer the momentum is the force, isn't it?
Yes, sir.
If the rate of transfer of momentum is force, so upon area becomes by definition pressure. Now the question is why per unit area? Why not only force? So the thing is, for any gaseous or liquid molecule, a bigger area means bigger impact. A large number can hit together, isn't it?
Yes.
Yes, sir.
So as you grow the size of the wall, a large number of molecules will be intercepted at once, and all of them will impart their momentum.
Yes, sir.
Understood? And because all of them will impart momentum, so bigger the area, bigger the momentum they can exchange.
Yeah.
So how to make the momentum exchange independent of area? By dividing by area. Because that becomes the characteristic. Now the area is not important, isn't it? So pressure becomes the characteristic. What is pressure now here? It is the ability of the molecules to transfer momentum per unit area per unit time whenever intercepted. See, they always have the ability, but to manifest the ability, you need to intercept. And walls are always there to intercept. But even there is no wall. If you bring your finger will be attacked by these molecules. You go to any exotic beach and there is a sea breeze touching your face. What you experience, that beauty is nothing but the infinite transfer of momentum on your face by the gaseous molecule. And it is like so tiny molecules that the impact is creating a kind of energy. It's giving you the rejuvenation. It is not hitting you badly, right?
Yes, sir.
But again, it is the transfer of momentum by these gas molecules on your face. So the molecules will have the ability, your face is like the interceptor, and the moment you intercept their path, you are the recipient of momentum. And so the amount of momentum which you receive per unit time, per unit area, we call it pressure. So what is pressure now? Tell me if you have understood. What is pressure?
Sir, pressure is the ability of a molecules or particles to impart momentum over when
Yeah.
intercepted per unit area,
Per unit time.
per unit time. Yes, sir.
Because the momentum upon time becomes force, and then upon area becomes And why we are trying to define current area? Because in case of gaseous system, a larger area, if you intercept by a larger area, you will get more molecules to be hitting there, right?
Yes.
So you want to make it a point calculation, not the area calculation. So you divide by area to make it a point function, right? So that is why pressure becomes the point function. Are you getting it what I'm saying?
Yes.
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 sir.
So that is the pressure for you. And the way we define pressure for the gas is the but obvious choice, because you talking about the momentum is again a difficult task. So again, if I draw something like this, let me show you something here. See, in the name of the chapter is kinetic theory of gases. If you really understand the theory, the chapter is over. So imagine this is the intercepting surface. Okay. And if you have this intercepting surface, if you consider a dot, if you zoom the dot, you will again see elementary surface, right? And this elementary surface will be hit by a single atom or single molecule or infinite number of molecules.
Infinite number of molecules.
So if I draw the graph of their velocity distribution, all will hit with different velocity, right? But on an average, the net momentum which you will receive over this area and any other dot will be same or different.
Same, sir.
So because you see, when we talk about the again momentum transfer, we talk about the momentum transfer over elementary area, not exactly dot. What is this? dA.
Yeah. Elementary.
So even if you distribute the entire surface into elementary dAs, every dA on an average will receive same momentum. Individual particle cannot impart same momentum. They will have different value. But in a cluster, you will get all sort of distribution, and therefore a cluster will have a constant value of momentum that it can transfer. So we wanted to know that how much momentum is transferred per unit elementary area per unit time. And because this is same for every elementary area, so we wanted to define this as a characteristic, and now what we call. See, we are just trying to create a macro variable. So what is pressure? It is a macro variable. It is macroscopic variable. Macro, not micro. Am I clear, guys? Tell me yes or no.
Yes.
Yes.
Yes, sir.
Yes.
So if you want to really calculate the pressure of any gas, you bring any random surface and calculate this value, you are done. That's it. Okay. So I hope the pressure is clear to all of you.
Yes.
Now, so we are almost at the end of the postulate, but just I would add something. Every system in the steady state will exhibit same pressure at every point, although individual molecules are not having the same momentum. Because when we define the pressure, we take some elementary area, and that elementary area will face a group of atoms or molecules, and this group will have symmetrical distribution throughout the volume, isn't it?
Yes, sir.
Yes.
So no matter where you introduce the surface, where you intercept the surface, intercept the path of the molecule, they will come as a group and will hit you and will let you share the same momentum over a unit time, over the unit area. So over the large time interval, the distribution attains some sort of symmetry. So you can say the distribution will be uniform throughout. There is a distribution, but that distribution will repeat similarly throughout the volume. Is this clear? Tell me,
Sir,
guys.
can you repeat the statement?
See, we have a distribution of molecule, velocity distribution.
Yes.
That velocity distribution will be same throughout the volume in steady state.
Okay, got it.
Then only we can define the pressure, yes or no?
Yes.
See, just like temperature, we can define when we have the same distribution across the volume. Pressure will also follow the similar process because every macroscopic variable can only be defined if system is having some sort of steady state behavior, isn't it?
Yes, sir.
So pressure is a macro variable, temperature is the macro variable, volume is the geometrical behavior. Understood?
Yes, sir.
So PV by T is what? A constant behavior. Okay. So PV by T is a constant behavior. Therefore, PV by T is always a constant behavior, and okay, constant behavior for per mole. And therefore, this behavior is called a universal gas constant, capital R, of value 8.314, or sometimes we also use 25 by 3. And that is how you got the first ideal gas equation. So now the question is, what is ideal gas? Oh, that's a big question. What is ideal gas? So a gas which follows the postulates of KTG is called ideal gas. Is this clear?
Yes, sir.
Yes, sir.
And only for the ideal gas, we have a well-defined pressure, well-defined temperature. The N is which you can dictate. V is something the shape will decide. So there are some statistical property, but we do have something called a geometrical property. So out of this PV NT, can you tell me which one of the following is statistical property? PV NT.
PNT, sir.
PNT.
So V is which property, guys?
Geometrical.
Geometric.
Geometrical. N is, of course, what you decide, how much you want to insert in the given chamber. Okay. And this ratio is constant for every gas. That's what this is called, the universal gas constant. But this is only true for which gas? Ideal gas. Okay.
Ideal gas.
And what is ideal gas?
That follows the postulate.
Yeah, which follows the postulates of
KTG.
KTG.
Now we know that in real life we have real gas. So what is the purpose of studying ideal gas? So certainly it is oversimplified, right?
Yeah.
Yeah.
And because it is oversimplified, so it is somewhat mathematically easy. And the benefit is if you go to the outer space, the atmosphere even exists beyond the ISS. Do you know this fact? The International Space Station, you know the height. It is in thousands of miles. The atmosphere is even beyond that. But the difference is it is highly rarefied. A highly rarefied gas will have a large intermolecular distance, and therefore though they have attraction, but they fail to interact. Why? Because the separation is too large. Understood? So even though it's a real gas, the behavior will be like ideal gas.
Yes.
So highly rarefied gas at very high temperature always behave as
Ideal.
ideal gas.
Ideal gas.
And that is why it is convenient to study
Ideal gas.
I,
Okay, sorry. So every real gas at high temperature and which pressure, low or high?
Very low. Low.
Very low pressure will behave as
Ideal gas.
Ideal gas.
ideal gas. So this is the ideal gas, and this ideal gas is only defined when two things are attained by the gas. The first is T is well defined. And when T will be well defined? When the system has attained the
Thermal.
thermal
Thermal stability. Equilibrium.
equilibrium, which means the two neighboring cluster will exchange energy, but the net change will be zero.
Zero.
So if every cluster is in thermal equilibrium with the neighboring cluster, so can we say the entire system is in thermal equilibrium? Yes or no?
Yes, sir.
So this equation is valid when the system has already attained the thermal equilibrium. P is well defined. When we say P is well defined, so this has to do with the Newton's laws of motion. And this is called the mechanical equilibrium. The rate at which the cluster 1 is transferring momentum to the cluster 2, at the same rate cluster 2 is transferring momentum to the cluster 1. Understood?
Yes.
And as a whole, you can say none of the cluster is losing any ability or any momentum. So every cluster will carry the same amount of momentum. And so whoever will intercept that cluster will get to see that momentum transfer and hence will experience the pressure. So pressure is experienced when intercepted, but pressure defines the ability to transfer momentum per unit time, per unit area. Understood? Okay. Okay. And then when n is defined? So when n is well defined, tell me.
Chemical equilibrium.
So n can be only defined when there is no rate of forward direction. You can say the rate of forward and equals to rate of backward direction. It means the composition of the system becomes constant. And if composition is constant, it means the concentration is also going to be constant. Yes or no?
Yes.
So if you bring that into context of gas, then Chemically, there is no reaction. Therefore, every constituent of the gaseous mixture is going to be same. Understood? And therefore, this state is called chemical equilibrium. And if a system is lucky enough to attain all the three equilibrium together, then that system is said to be thermodynamic. Oh, chemical is understood. Equilibrium. So a system is said to be in thermodynamic equilibrium when it attains all the three equilibriums simultaneously. Understood?
Yes.
And when a system attains the thermodynamic equilibrium, then it will have well-defined P, V, N, T, and these variables is called thermodynamic coordinates. Just like we have a three-dimension X, Y, Z coordinate, you can also create a thermodynamic world in which I can say P, V, T are the three coordinates. And every point in this universe is called a coordinate. And a coordinate will have the finite value of X, Y, and Z. If you change the coordinate, then at least one of the value will change, yes or no? Is it possible to have all the three values same for different point in this three-dimensional space?
No,
No.
sir.
At least one of them must change, isn't it?
Yeah.
Yes.
So every 2 point in space will have two set of coordinate. Similarly, every 2 point in the thermodynamic world will have two different set of P, V, and T's. In worst case, two of them may be same, but at least one of them must vary. Otherwise, they will represent only the same location, same coordinate. And one set of values which we require to represent in the PVT world, assuming n is constant. This is called state of thermodynamic system. So we say that our system is in a thermodynamic state with a well-defined P, V, and T. And therefore, you can write the ideal gas equation PV equals to nRT. You can also write the ideal gas equation P dash V dash equals to nRT dash. And when you go from this state to this state, you can follow some path. The path can be any random path. So the path which you follow, if it is following the path, okay, I'll show you. It's pure mathematics. Very interesting. So in the PVT world, okay, now the simple question is, can we go from one point to other point without passing through intermediate points? So can I go from here to here directly? Tell me common sense. Can a system or gaseous system can attain one state and then another state without going any subsequent states?
No, sir.
No.
No.
So to go from one state to another state, how many you can say how many intermediate state you will pass through?
Infinite.
Infinite, correct. Now, it is not necessary that at every point the system is maintaining the thermodynamic equilibrium. What I'm saying? It is not necessary that while going from this equilibrium state to this equilibrium state, you're also maintaining the thermodynamic equilibrium at every intermediate position. It is not necessary. Understood what I'm saying? So it is quite
Yes.
possible that you have a steady state, then you shake the container, you disturb it, you heat it randomly, and then after coming to the state 2, you leave it for some time for settle down, and it will eventually state the equilibrium configuration. So state 1 is well defined and 2 is well defined, but can we guarantee that every point on the path is well defined?
No, sir.
We cannot guarantee. When you do not guarantee, we call random process. So what is random process? When the intermediate stages are not well defined. It means I cannot tell you what is the PVT here. It will have some value, but we don't know. But what if we can well define? In a way, a random process cannot be shown. I mean, it's a bad thing. So we have 1 and we have 2. That's it. And we fail to represent the individual point of the process. So we know this is P1, V1, T1, and we know this is P2, V2, T2. But because it's a random process in between, so there's a question. This set of values and this set of values will have any relation or cannot have any relation. Is there any chance of P1, V1, T1 and P2, V2, T2 relation?
No, sir.
The answer is no.
No.
There is no question of relation. Relation is only possible when every subsequent path of the journey is well defined. So when every point of the journey will have the well defined values of P, V, T, it means even though system is at this location, it is at thermodynamic equilibrium. Even though system is at this location, the system is at thermodynamic equilibrium. Even it is here, it is having a thermodynamic equilibrium. When this process always maintain the thermodynamic equilibrium, then we call it thermodynamic process. So do you realize the difference of the thermodynamic versus random process?
Yes, sir.
Yes, sir.
Now, in a real life, this is most common process. Because let's say you have a gas in a container, you suddenly throw a matchstick or a burning lighter or maybe a hot coal. You throw it. So the temperature of the every corner of the container will have same value, or it will be more near the coal and less away from the coal.
Sir, more near the goal and less away.
Exactly. So is it having the symmetrical distribution of energy? No. So can we define temperature for that system? Answer is no, because temperature is variable at every point, isn't it? But if you leave the coal for a maybe long time, then it is quite possible that eventually they will have a uniform distribution of temperature, isn't it? So if you throw a large amount of coal, the difference will be very random. It will have a vigorous, circulation of air or the gas, and it will try to, have a uniform distribution as soon as possible. So a random process, in a random process, the initial and final states are in equilibrium. but the intermediate states are not in equilibrium, hence cannot be defined. So intermediate states are not defined. Only initial and final are defined. So what is thermodynamic process? Tell me, guys.
The intermediate states are also well defined.
Very good. So when you go through such process in which everything is well defined, then you will get a graph actually. And this graph is called indicator diagram, which indicates how the changes has taken place. So the name is indicator diagram. Now, what I said, in real life, the processes are thermodynamic or random. What do you think?
Random.
So real life is always random. So the question was, how we can have a thermodynamic process? Because the real life is random. So the answer is, carry out the change at elementary level, which means from P only go to P plus dP. From V go to V plus dV, or from T go to T plus dt. If you go at elementary step ahead, then the changes will be at a very small scale, and therefore it won't be very difficult to attain the equilibrium. Because this is the condition to maintain the equilibrium in a thermodynamic process at every stage. So this incremental change we termed as quasi-static process. A process in which the changes are always elementary at one time is called quasi-static process. Quasi means almost stationary. Quasi what means almost. Okay. So quasi-static, it looks like static, but it is changing. So that's why the word quasi has come into picture. So every well-defined thermodynamic process are which process?
Quasi-static.
Yeah. Every thermodynamic process in nature are by default quasi-static process. Okay, anyway. So the idea of state is clear. What is state? What is state coordinate? So PVT together is called state, and PV and T are called state coordinate.
Yeah.
So one set of values is one state. Other set of values is a new state. And in every set, what you see individually is called
Internet.
coordinate. PVT is called what?
Coordinate.
Thermodynamic coordinate. Understood?
Yeah. Got it.
And PVT as a together, one set of value is called
State.
one state. So what is phase? The last concept. What is phase? Come on, phase is solid liquid gas. So in physics, the meaning of state and phase are quite different than in chemistry. In chemistry, you may use solid state, liquid state, gaseous state. So the word state in chemistry is actually phase in physics. So physics is always more accurate. Okay, understood what I'm saying?
Yes, sir.
Yes, sir.
In chemistry, you call this as state. But remember, in physics, the word state having quite different meaning. So what is meaning of state in physics?
PVT took together.
State is defined for a thermodynamic system, okay, in which the thermodynamic coordinate will have a fixed value. So one set of thermodynamic coordinate required to explain a thermodynamic system is called its state. Okay, I'm not
Yes.
going to define all this. I mean, just listen to this. I'll share a note, you can read about it. So this KTG is all about what? So we are going to bring back the PNT through the use of KTG. Understood? Yes.
Yes, sir.
And that is the whole purpose of learning KTG, because once you understand the KTG, the first law is simply a consequence of KTG. From KTG, we can derive the entire first law. And once you understand the first law, the second law is just time pass. I have discussed what is second law. It is entropy, right? Okay. Anyway. So now we are going to, okay, I hope the postulates are clear, guys.
Yes, sir.
And also remember that the last postulate, the motion of gaseous molecule is not affected by the gravitational force. So gravity will never affect the individual motion. Gravity can affect the motion of center of mass of the system. That's it. So I'll put into words, gravity never affects the motion of individual gaseous molecule, but it can affect the center mass. CM, I hope center mass are like center of mass of the motion. Also, I'll mention so internal kinetic energy of gaseous system is the kinetic energy of system in the system as seen in CM frame, the center mass frame. Have you heard this name, center mass frame? Have you heard this name? Tell me yes or no.
Yes, sir.
Yes.
Simply, when you see the things from center mass, then what you see is the internal energy. If you don't see from center mass, what you see is the internal energy plus center mass energy. Okay. So anything important we need to explain? What is pressure? Okay, I'll explain this pressure. Pressure is the ability of gaseous molecules to impart momentum per unit time per unit area whenever intersected by the surface. I hope this is clear to all of you. So KTG is clear, the postulate is clear. Yeah, I think these are important facts. What is temperature? Temperature is the representation of average internal kinetic energy of system. But I have already mentioned that the internal energy of system is the kinetic energy, isn't it? So can we say that internal energy itself depends on temperature,
Yes, sir.
or internal energy of any ideal gaseous system is function of, not function, is proportional to, I can say, is proportional to temperature. So temperature is a very fundamental quantity. So before the invent of, you can say, KTG, before this model, okay, and to be just for your information, the guy who gave this all postulate and all this idea was you can say ostracized by the scientific community. People said him mad, that gas will have molecule and they collide. So he was called madman of his era, and he died out of depression, possibly suicide. And this man was none other than the Ludwig Boltzmann, which is in his honor we have the Boltzmann constant, right? KB. So he was the pioneer of this statistical physics, and he was much ahead of his time actually. So anyway, whenever you are much ahead of your time, people will say you mad only. Okay. So the temperature is clear. What is temperature? What is pressure, guys? What is internal energy? Everything is clear.
Yes, sir.
So now comes the most important part. Derivation of pressure in a gas. So this is the container. You're always free to draw the elementary volume in the container. Now the question is, sir, why elementary volume? Why not the entire container? Because a molecule is not able to move such a large distance, right? Because as a molecule will try to move, it will hit the neighboring molecules, isn't it? So every atom or molecule in a gas will travel for a very small distance, and it will make an impact with the other molecule, will collide with the other molecule, and it will change the course of direction of its path. but a molecule will never go far away. So most of the motion of the molecule is localized. Although it's random, but it is localized because it is always getting hit from all the directions, isn't it? And the same is true for the other molecules. So in general, you can say the motion is, always localized with some exception. So some molecule do make their way far away in the container, but you can say majority of molecule live their life in its vicinity, in its locality. So the question is, as we inject more and more gas into this container, a molecule will get less space to travel or more space to travel. The answer is, as you inject with a large number of gases, as you increase the mole or the concentration, the total space left for a molecule to travel will be less or more? Hello, tell me.
Sir, lesser, sir.
So every molecule will travel now less because they don't have they don't have more free space. They have lesser free space to travel. So there is a term called free path. So the distance a molecule travels before, impinging on other molecule, the distance which you travel on a straight line, this is called free path. And because if you try to think of every individual molecule, can we say every molecule will have different free path? Isn't it?
Yes.
And therefore, if I try to, go for a cluster and try to find the free path for every molecule, it turns out to be different. And therefore, we define a term called mean free path. So mean means average, and free path, as I have explained. What is free path? It is the distance traveled between two successive collisions. Understood? What is
Yes,
free path, guys? It is the distance traveled between two successive. It is the mean of, because we have found mean value. So free path is the distance between two successive collisions. If you take the mean of all such values for the cluster of molecule, what you end up is getting mean free path. So it is the mean of or average of distance traveled by a molecule between two successive collisions. Is this clear? So it is the mean of the distance traveled by a molecule between two successive collisions. So how we represent by symbol? So there is a lambda. Lambda means a distance actually. And you can say lambda is lambda 1 plus lambda 2. Dot 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 for lambda of the n molecules. So now the question is, on what factor lambda depends? The answer is
number of moles.
concentration.
Yes, sir.
Only concentration, nothing else. So depends on molecular concentration. Now the question they will ask you, does it depend on temperature, pressure, or anything else?
No, sir.
No, because it is just like a spacing. So as you put more molecules per unit volume, it will change. But if the concentration is constant, so whether they move fast or slow doesn't matter, right? Now between two successive collisions, you will spend some time, right? That's called the time of relaxation. So what is mean time of relaxation? So we represent by symbol tau. Tau is defined as. Come on, guys. I have explained in the current and electricity also, right?
Sir, the time, I mean, like the average time elapsed between two successive collisions.
Correct. Correct. So as I increase the temperature, what will happen to tau? Will it decrease, the remain same, or increase?
Decrease.
So the lambda is finite, isn't it? Lambda is finite, but as you have more temperature, it means your kinetic energy has gone up. So if you are moving faster than before, it will take less time to travel the same mean free path, isn't it? So mean time of relaxation depends on temperature, yes or no?
Yes, sir.
But lambda does not depend on temperature. So tau depends on lambda and temperature both, right? So it is basically lambda upon V average. That approximately. So the distance upon speed is called time. So if you take the average velocity, and if you divide the mean free path with the average velocity, what is get is the mean time of relaxation. Because everything is the average, no? Average, average, average. Okay. Now
Yes.
lambda and lambda and tau are called again statistical parameter. So anything which we define as average, RMS, most probable, all are statistical variable. These are mathematically defined things for the purpose of study. Now, what I was saying that okay, let's out of the big container, you take out elementary volume and think elementary volume as a cube. So I have taken the elementary volume such that the L is less than lambda. Because if I assume L more than lambda, what will happen? It will undergo multiple collision, isn't it?
Yes.
You can only move freely up to lambda, no?
Yeah.
So if I have a container with more than lambda size, you will undergo multiple collision, isn't it? Okay, not getting it. If the size of
Sir.
container is more than lambda, it means
Yes.
while you travel from one surface to the other surface, you will make more collision with other molecule. You will
Sir,
make
but in this
yeah.
case,
Yeah, in any case.
sir, no, sir, but in this case, when it is less than lambda, what will happen? Sir?
It can move straight line without getting disturbed.
Oh, okay, sir.
And then I create this hypothetical boundary in our mind. So let's say this is the hypothetical boundary. So every molecule can travel from here to here and come back and then hit here and then come back. See what you're trying to understand, the ability, no? Ability is going to be same, isn't it? The
Yes, sir.
ability will be same, no? So I'm taking a cube. I can take any shape. Again, cube is convenient. So think this way, the way I'm saying. Imagine a container, and the most important part of this chapter is the derivation. You must master the derivation. So I would like to understand the momentum imparted to this surface only. So for that reason, I'm going to take this direction as x-axis. This is origin. Y-axis. Oh, maybe like this. Anyway, z-axis. So since I would like to know the momentum imparted to this shaded surface, so we have a molecule here, and let's say, see, a molecule is free to move in any direction. So can we assume the component of velocity in the x as Vx, Vy, Vz? Okay. So imagine at one time we have only one component, the x component. What is the initial momentum of the molecule? Can we say mvx? M is the mass. Tell me guys, can we say mvx? Yes or no?
Yes, sir.
Yes, sir.
Now this is a ball. So you come with mvx, you hit the surface, and you bounce back with the same speed. Because the collision is going to be perfectly elastic, isn't it? So what is the final momentum of the molecule?
Yes, sir.
What is the change in momentum by the collision? Only value wise. Changes how much?
2 mvx.
So how much momentum is imparted to the surface? The answer is 2 mvx. No?
Again 2 mvx. Yes, sir.
Now the question is how to calculate the time. So for a discrete collision, the time is defined as the time between two successive collisions is called delta t. So when you hit for the first time, so when the molecule will make an impact here, it will bounce from here, will go back and will again make a bounce here. So the first impact is here. Let's call t equals to 0 here. It will go back, bounce with from the back wall, will come back and again make the next bounce. So first is 0, second is delta t. So what is delta t? So how much time it will take to go from the shaded surface to the back wall? How much time will it take? L by Vx. To go from
Yes.
here to here, you will take L by Vx, and to come back again L by Vx.
Yes.
So the total time interval before two successive collision with the same surface is how much? 2 L by Vx, isn't it?
Yes, sir.
Yes.
So can we say that this momentum change was persisting for this interval? Yeah,
Yeah.
we can say. So we define what is the average force imparted by the molecule on the surface on the X. So the average force is from Newton's second law delta P by delta T, right? Isn't it?
Yes.
So what is delta P?
2 MVA. 12 by Vx.
The answer is,
Okay.
it is very simple. mvx square by L.
Yes.
So what is the pressure on the wall X? What is upon?
Area.
Area.
L square.
So depending on if it is a L, I mean, if you take a cuboid, then it will have some X, Y, and something else, right?
Yeah.
Anyway. So if you substitute the average force,
Mvx. L.
it
Yeah.
becomes L cube. And L cube is nothing but the volume of this container, right?
Yes.
So can we say the pressure, which is the right wall will experience on an average, is how much?
Mvx square by V. Capital.
But this is the analysis assuming that the molecule is going towards X,
Yeah.
but it can go along Y also. No? So similarly, if you would have analyzed for the Y side, Y axis, the Py must have been how much? And Pz equals to, you know why we are able to write all these three equations? Because the nature follows symmetricity. And in any system like gaseous system, every event is equiprobable. So can we say that a Px is more probable than Py and Pz, or all are same? Tell me, guys.
All are same, sir.
So all are same, isn't it?
Yes, sir.
And therefore, the total pressure that the molecule can exert is neither Px nor Py nor Pz, but 1/3 of all these event. This is called the actual pressure. This is the actual pressure exerted by single molecule. Because we are realizing, I mean, defining the only one molecule, right? So this you can write as one. What is the 1/3? It is the probability that every event is equiprobable, right? Understood?
Yes, sir.
Am I audible to you guys?
Yes.
Yes, sir.
So you can see that 1/3 has come from the theory of probability, because these events are not going to occur individually. Rather, we would take the event as per the probability. So this is only 1/3 probability that this will occur, or this will occur, or this will occur. So when you use the word or in a theory of probability, what you do? Addition, right? Event A or B or, and when you use and, then
Multiple.
you multiply. Okay. So that's why we have the probability, and because every probability is equal, so the actual probability is sum of the 1/3 of each term. And if you do so, the term m by v we can take common. What we are going to get? And what this represents? It represents the square of the actual speed of the molecule, right?
Yes.
So pressure of each molecule is 1/3 of mass of molecule upon volume into speed square, right? But in a gaseous container, how many molecules we are going to have? A large number, isn't it?
Yes.
So if I talk about the cluster, because if you remember, we define pressure for the cluster, right? One cluster. So
Yeah.
in one cluster, if I assume there are n molecules, and the same will have the repetition. So can we say the pressure of the first molecule will be 1/3 of, I'm assuming all are identical in the cluster, let's say. So can we write this as V1 square? So in the same cluster, we have something with V2 also, right? So the third will have how much? Tell me, guys. And also tell me if you're not getting something. So if I continue with the nth molecule for the cluster, what I'll get? So what is the total pressure of the system or that container? What is the total pressure? Now this P is different from that P. So that P we were deriving for each molecule. Now we have the total P. So total pressure is how much? Can we simply say summation of all pressure? Isn't it?
Yes.
And that's why this is called the Dalton's law of partial pressure. So in a gaseous system, if you have a mixture of gases, then every component of gas will exert its own pressure based on its fractional value of moles, right?
Yes.
So the total pressure turns out to be how much? Okay. So let's call P total as P. I mean, there's so much P and it's confusing. We have started with the single molecule and now we are going to generalize it. So this part is done here. So for n molecules in cluster, so let's call P total as P. So the total P turns out to be how much? 1/3 of m by V. V1 square plus V2 square plus what? Can we say Vn square? Tell me, guys, yes or no?
Yes. Sir.
Yes, sir.
Yes.
And now we are done. So we got the total pressure equals to 1/3 m by capital V So P into V is how much? So you can see something really nice. 3 times PV is how much? So if I divide by 2, it is 1 by 2. And you can see clearly that every term is now representing what kinetic energy formula of every molecule. Yes or no?
Yes, sir.
Yes, sir.
So is this term representing the sum of kinetic energy of the entire system? Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
So this term is actually called the kinetic energy. And the formula turns out to be how much? 3 by 2 PV equals to KE. So now we have proved. And what we have proved? That kinetic energy, now we'll write the kinetic energy by symbol capital E. Left. So the capital E we can attach 3 by 2 PV. And because we know that the PV equals to nRT for any ideal gaseous system in thermodynamic equilibrium. So can we say E equals to 3 by 2 nRT?
Inert. Yeah.
Yes, sir.
Yes or no? Tell me guys. Is
Yes.
this
Yes,
clear?
sir.
Yes.
And since I have explained to you that the internal kinetic energy is nothing but the internal energy of the gaseous system, and because we write the internal energy by a symbol capital U, so all are same. No? So can we say capital U is also 3 by 2 PV?
Yes, sir.
And can we say this is 3 by 2 nRT? Now all
Yes,
is
sir.
only matter of it is just a matter of calculation, isn't it? So
Yes.
all these are having interpretation. If you understand one thing, the rest is simply the way to write. So the formula U equals to 3 by 2 nRT is giving you the kinetic energy of the system. Which kinetic energy? Translational, rotational, vibrational, which one?
Translation.
Correct, because we only describe the Vx, Vy, Vz, right? So we never took the moment of inertia or omega, right? So
Yes,
whatever
sir.
we have derived is the translational kinetic energy. Some other form of kinetic energy will also come into picture. We'll see very soon. So internal energy symbol or formula is clear to all of you guys.
Yes.
Yes.
Let's go back to the kinetic energy. So if I call the equation 1. So 1 implies kinetic energy was how much? 1 by 2 m v1 square v2 square dot vn square. Correct? Now this way of writing is not convenient. So in mathematics, we define the average of squared value. What do we define? Average of squared value of velocity or speed, you can say. So we define something called average of square. And then you take the root. So when you square a function, you take the average and you take the root, what we call RMS value. And RMS means root mean square, right? Root mean square. If you read in a reverse process, reverse wise, so square the value, take the mean, and because you have squared, so take a root again. Move this way, you get the RMS. So by definition of a VRMS, square the function, find the average, and take the root. So this term is called VRMS. Does it make sense to you guys? Tell me.
Yes, sir.
Yes. Sir.
Is VRMS a physical definition or a mathematical definition?
Mathematics.
Mathematics.
And the most probable is physical or mathematical?
Physics.
It is a physical definition. So average and RMS are a mathematically convenient way of writing something. There is no physical meaning to it. But the most probable is a physically defined quantity. So make sure that you understand the difference between the mathematics and physics. So VRMS is a convenience. Understood?
Yes.
So sometimes it is also useful in the calculation of standard deviation or the variance, because if you know the standard deviation, it is something like this, isn't it?
Yes.
So VRMS is how much? Is squaring the value,
Taking the mean.
taking the mean and the root. So can we write the square value as n VRMS square? And therefore, this equation, this kinetic energy equation, this equation, let's call equation 2. The 2 will transform into what? So the kinetic energy we can write as half m n
VRS square.
VRMS whole square, right?
Yeah.
And m is the mass of each molecule. N is the total molecule. So Nm is the total mass, right? So this m into m is the total mass of gaseous system, right?
Yes, sir.
Yes.
So you can say m total. So very simple. And this is how much? Again, 3/2 PV,
Yes.
isn't it? There are many ways to manipulate. So this is 3/2 PV, or you can say this is 3/2 nRT, isn't it?
Yes.
Yes, sir.
I mean, there are many ways. So you can write as total mass into VRMS is how much? 3 nRT. Why I'm writing like this? No, not required. Anyway. So we have the answer. How much? This kinetic energy was how much? 3/2 PV, right? Isn't it? This cancels out. So total mass upon total volume into VRMS is called, can you say this is 3P?
Yes, sir.
And total mass upon total volume is called what?
Density.
Density. So given the density of a gaseous molecule, can you find the RMS velocity?
Yes.
The answer is 3P by
Rho.
rho. So here comes the ways of writing things. Okay, you need to learn the manipulation. And it's difficult to remember the formula. You have to practice at home all the formula, then always manipulate from here to there. So I'll teach you some of the manipulation which you should be aware of. PV equals to nRT. N is called mass per molar mass. M means total mass. This M here is total mass. So PM equals to, so we all know the formula that PM equals to rho RT, correct?
Yes, sir.
Yes.
So P by rho is always RT by M.
Yeah.
This is conversion formula. So VRMS is how much?
Under root
RT
3RT.
by M.
RT by.
This is the proof of the VRMS. Understood?
Yes, sir.
Yes.
Now we need to define something called Boltzmann constant. So what is Boltzmann constant? R by Avogadro number.
Yes.
Understood? R by
N. F.
N. So VRMS and molar mass is defined as Avogadro number into molecular mass. So what M is called? Molecular mass. What capital M is called? Molar mass. The distinction should be very clear. So molar and molecular mass is clear. Molecular means mass of individual molecule, and molar means mass of one mole of such molecules.
Yes, sir.
I hope this is clear to all of you.
Yes.
So the VRMS having the formula how much? Either you say T P by 3 P by rho or 3 RT by capital M or 3 KT by. It is very easy to remember. R always comes with molar mass and K always comes with molecular mass. Does it make some sense to you guys? Tell me yes.
Yes, sir.
Yes.
Yes, sir.
So PV equals to nRT is one way of writing, but we also have the PM equals to rho RT. There's a third way of writing as well in terms of number. So again, PV equals to nRT, but N we can write as capital N, the number of molecule upon Avogadro number. Isn't it? We can also define the small n, this n. So n we can define two
Yes.
ways: count upon Avogadro count and mass upon molar mass. Both are same definition, right? I hope you can understand this simple calculation. So here you can clearly see that the P becomes N by V R by NA into T, and therefore N by V is called concentration. It is not the molar concentration, it is called molecular concentration. R by N is called Kb. Why it's close to my name? CKP is the CKT. P equals to CKT. So C is called molecular concentration. So molecular and molar are quite different terms. They're not the same. So in different contexts, you have to write things differently. So P can be written in multiple ways. PM equals to rho RT, P equals to CKT, and PV equals to nRT. So if you really want to master this chapter, you have to be master of manipulation. If you can convert one formula into other formula easily, you can really master this chapter. So let me summarize the formula that we have derived so far. So what we derived today, we first derived the kinetic energy equals to 3 by 2 PV and by default this was translational kinetic energy. So kinetic energy becomes a translational is 3 by 2 PV and it is nRT. So we got kinetic energy in different format. We derived the VRMS. So depending on what you know, now the question is when you substitute the M, it must be in kilogram mole per. So how to substitute variables. So T must be in Kelvin, not in degrees Celsius.
Yes,
R,
8.3.
314 what? Joule per
per
mole
mole.
Kelvin. Okay. Understood.
Yes,
Now this is the okay. If you think dimensionally, K means what? Energy dimension. Understood.
Yes, sir.
And PV must have the same dimension as energy. Dimensionally, they must be same.
Yes.
So always remember that P into V represents dimension of energy. Understood?
Yes, sir.
Yes, sir.
So PV is always energy. So if you want to think energy, so PV is energy. So nRT is also dimensionally
Energy.
energy. So you need to understand that when you multiply nRT, so RT must be energy, right? Because N is dimensionless, isn't it? Yes or no?
Yes,
No,
sir.
N is not dimensionless. N is having, my bad, N is having the separate dimension, the mole. So anyway, you can see from here, the formula is joule per mole Kelvin. So if you multiply R with mole and R with K, it becomes joule. Anyway. How to substitute capital M? Mole per kg. Small m in kg.
Yes.
So if when you are substituting a small m value, you need to put the actual value in kg. Understood? No?
Yes, sir.
Yes, sir.
What is the value of K, by the way? So K is how
R
much?
by N.
What's the value?
Oh,
R is 8.314. N is 6.022. The R by N is, you have to remember this answer, 1.38 10 power minus 23. Understood?
yes, sir.
Joule. What? Joule
Kelvin.
per Kelvin.
yes.
I think that's correct. No. So when you multiply K with temperature, what you get? K into temperature is
Energy.
energy. Okay, anyway, we'll come to that. So all these values you must remember. If you're not remembering these values, it's difficult for you to solve the methods. Okay. So a small m, capital M, meaning how to substitute. Density will be in kg per meter cube, right?
Permitted.
Yes, sir.
Yes.
And the pressure will be in Newton per meter square or Pascal.
Pascal.
Not in atmospheric, right?
Yeah.
So
Yes.
1 atm is how much?
10⁵.
10 raised to 5 to 10 raised to 4.
Pascal. Yeah, 1.01 into 10⁵.
Okay.
Yes.
So you need to remember all these things. Then what else you need to remember? What is 1 atm liter? So pressure into volume is always energy, right?
Energy.
So you're
Yes.
supposed to remember this answer. 1 atm liter. So 1 atm is how much? 10 power 5 roughly. Newton per meter square. And how to express liter into meter cube?
10 power minus 3.
10 power minus 3.
Meter cube, right?
Yeah.
So what you left with? 10 power
10
2 Newton meter, and the Newton meter is called joule.
joule. 100 joules.
So you must remember that 1 atmospheric liter is 100 joules. So when you're solving question in which pressure is in atm and volume in liter, don't disturb it, solve it that way. At the end, convert this way. So I hope you can remember this. 1 atm liter is
100 joules.
100 joules, right?
Yeah.
Clear to all of you?
Yes.
Yes, sir.
Okay. So next we can define okay. So now we have seen a variety of formula and how to write these formulas, how to manipulate these variables. So the next is called degree of freedom. So what is degree of freedom? Should we continue the next lecture? Tell me, guys. It's 1 o'clock already. So we'll take care of the degree of freedom in the next lecture. And then we can keep on deriving. So what your duty is, go home and derive the pressure derivation at least 10 times till you realize it. And then
Okay.
you can do one more question as a derivation practice. So imagine there is a snooker or billiard table, and the number of balls are infinite. And there is a side support. So now here, instead of 3 dimensions, we have collision only from the side support, right? 2-dimensional collision, isn't it?
Yes.
So develop a KTG model. It's called XY. And imagine we have a ball, infinite balls everywhere of mass m each. So here the pressure will be, let's define something called linear pressure. I mean, it's a very strange term, linear pressure, which means force per unit length. So in general, how we define force per unit area, right? So in this 2-dimensional world, I will create a new definition of pressure, which says force per unit length. And if it is so, you can choose x-axis this way and y this way. Now there is no z component. Okay. So this will have only vx and vy. Okay. And you're supposed to create a pressure formula the way we derived. Okay. You can take n molecules on this table, and you can define a concentration C as n upon. So there we were defining density. Here we have the surface density. Sigma, you can name it sigma, surface density. And you can define n by xy as sigma. So your question is, can you derive the new formula of pressure? Okay, that's your question. And then you can continue this derivation for a 1-dimension question in which molecule can only move along this. Here, I won't ask you pressure, I'll ask you, can you define the force? Let's say it is fixed. L is the length. So what is the average force exerted by the molecule on the wall? So these are 3 questions that you should be aware of. And all 3 are potential questions of J advance. So JE has already used this formula. And those who are good with the KTG, they solve this question. And perhaps it was one of the most challenging question of a J advance. But it's very easy if you know the simple derivation from the idea of KTG. Okay. So try these 2 questions as a homework. In the question 2, you have to find pressure as a force per unit length. In the other question, you have to find the force itself. Okay. And here length means length of the edge. This L is representing what? Length of the
H.
edge. Because as the length will grow, more molecules can hit together, right?
Yes.
This is how you could think about. And this question. So we have solved the 3-dimension here. So the only difference is in 3 dimension, we have to take 1, 2 by 3 in 2 dimension, it will become what? Px plus Py by
Two, sir.
2. And in 1 dimension, it is P only, like the what we got. That's it. So 1 dimension is the answer which you know already. What was the answer if you remember? The force was
mvx square mv square.
so here Vx is V only, na, right?
Yeah.
And we don't have any other event, so we just have only one event. So the answer is mv square by L.
Yes.
In the case 2, what you will get? You will get something interesting. mv square by 2, right? Because the last case we got 3. So try to derive it in terms of sigma. Sigma is a nice way to explain the answer. And then I will show you the use of this formula. So all at the see the theory, if theory is clear, then you won't find this chapter at all difficult. So if you really understand what is pressure, what is volume, what is temperature, what is state, what is phase, what is process, what is random process, what is thermodynamic process, then that is more than enough to deal with this chapter. So after next lecture, I'll at the end of the next lecture, I'll show you the JEE mains question, that how easy is those questions you can solve mentally. Okay. Not all questions. Some questions requires more effort. Some questions are easy enough to solve mentally. All right, guys. Good night. Take care.
Bye, sir. Thank you,
Bye,
sir.
sir.
Good night,
Thank you.
sir. Thank you,
Good night.
sir.
Good night.